Today, I'm going to talk about Chapter 2 exercise. An outcome table lists the various possible outcomes of a set of similar or related events. Here, we're using binomial distribution as an example. This base R function, R binom, helps generate random numbers that follow an binomial distribution. We set n equals to 100. We can see exactly we have 100 numbers here, and you can think of this as 100 trials. And size equals to 6 means we do experiment 6 times for each trial, and the probability of us getting our desired outcome is 50%. So for the first trial, among the 6 experiments, we got 2 desired outcomes. And the second time, we got 5 desired outcomes out of the 6 experiments. Table is a very handy base R function that helps you give you a quick summary of the distribution. So you can see here 0 showed up 4 times, so 1 showed up 9 times, and 2 showed up 22 times, right? One thing I want to mention is when you run this, each time you will get a different result, and that is because the R binom function involves a random process. Because it generates random numbers, right? So each time, even though these numbers should follow binomial distribution, but they can be very different. That's why setting a seed can be useful here. When you set a seed, basically you R eliminates the randomness here. So each time you will get the same result. This seed can be any number. It doesn't really matter for the purpose of generating the same result. This is particularly useful when you do your homework. You want to have the same result, so your explanation makes sense, right? Because if you get a different result, then the explanation you wrote for the previous result wouldn't make sense anymore. So here you can do a histogram, and the y-axis would be the frequency, means how many times, what the count is, right? We can create a nicer display by using a bar plot instead of histogram because there are no intermediate values. So here, no intermediate value means this is a discrete variable, not a continuous variable. So this part stayed the same, and you just do a bar plot. So each bar would represent a number here. The first bar would represent 0, the second bar would represent 1. If we divide each value in the table by the total number of trials, we can see the bar plot. We can use the bar plot to display probabilities instead of counts. This is fairly pretty straightforward. One thing I want to talk about is the reason that it is okay for you to divide a table. This is a table, right? By a number is because if we assign this table to TBLE, and you check the names of TBLE, you will see, one second. If you check the names of TBLE, you will see 0, 1, 2, 3, 4, 5, 6. And this means for the number 13, we name this number to 0, and we name 92, the second number, to 1. And we can change the names of TBLE by assigning, you can use equal mark here or this thing, to different, you can rename the names from numbers to letters, actually, right? If you check TBLE again now, these numbers 1392 are named to different letters. And we can also do unnamed. When you do unnamed, the names are gone. Only left with numbers. Let's go back to TBLE here. And if we XOR, so if TPLE is an array, so if this thing here is an array, it returns true. So TPLE is just simply a list or an array of numbers with different names. So essentially, it's still a list of numbers, right? So that's why it is okay for you to divide by a list of numbers by 1,000. R, in this case, will perform vectorized computation. So, which means each element of the TPLE, each element of this list or an array will be divided by 1,000. I just want to quickly explain why it is okay to divide a table by 1,000, right? Now we want to do a bar plot for the probability. So as you can see here, instead of counts, now the y-axis shows the probabilities. Another really useful base R function is called CombSum. So now we assign this table, probability table, to this thing called prop table. And CombSum means cumulative sums, right? So the first number would stay the same, and the second number would be the sum of the first one and the second one, and the third number would be the sum of the first three. So the first one plus second one plus third one. All right. This is the cumulative sums table, and this is the original one, the original probability tables. And this is the plot for the cumulative sums of probabilities. As you can see, the last one is 1 because if you add all these together, you get 1. The cumulative sums bar plot and table allow us to reason about a range of outcomes, right? For example, what the probability of having 2 or fewer jelly down toast drops. So then this would be either 2 or less than 2, so fewer than 2, which is 0 and 1. So this is the sum of the first 3 numbers. Okay. Contingency table displays more complex and linked outcomes. Must have at least 4 cells with at least 2 rows and 2 columns. Let's make our own contingency table here. So the way that we make a contingency table is by creating a matrix. For the stats major and math majors out there, when you do a matrix multiplication, R is a really good calculator. Personally, I used R to calculate matrix computation a lot when I was in school. Here, this one argument I want to point out by setting by row equals to true, you are filling the number into the matrix, right? 2, 1, 3, 4. However, if you set this to false, you'll see now it's 2, 1, 3, 4. So it's filling the matrix column wise. This is something I just want to mention. So if in order to have the right matrix, you want to make sure to set by row to true. And you can name the columns and the row names by assigning names into the call names and row names. Right? So let's go back to here. So this is still a matrix, but then we can do a table. Then we're converting the matrix to a table. This is the way to calculate the grand total of toast drops. So add all these four numbers together. We can use a function called margin.table. Let's see here. See, we have 10, which is the sum of all these four numbers. Or we can do margin.table toast 1. 1 represents rows and 2 represents columns. So when you do 1, we will do a row wise, right? So 2 plus 1 and 3 plus 4, a row wise computation. We can also do something like row sums. This function can also help us to calculate. If we do this, we also get the same result. So row wise sum. And same thing as call sums. Right? It's the same thing as this function here. You can use either one. And so for matrix, we can also do a matrix-wise computation. So each element of the matrix here or the table here can be divided by a number, right? So when you do this, let's check the table. So each number, each element of the matrix here is divided by margin table toast. If you remember, this thing equals to 10, right? So 2 divided by 10 give you 0.2. Same for the other four numbers. You can also do something like, let's go back to here. Actually, we're not going to talk about it here. And we have how to rename columns, right? We can, for the call names for a data frame, I believe that my data frame isn't defined. So we can just use, let's see. So we can just use our base R data frame here. Let's use this very popular base R data frame called Iris. So you can, let's rename this base R data frame to my data frame. And for the column names of Iris or my data frame, we see there are 5 columns, and we're using index to subset, right? We are using the index here to abstract the column name that we want. And this index is 2, which means we want to get the second names out of the column names, which is this one. And we can reassign a different name into it. So now this name here is replaced by C2. Now, if we look at my data frame, the column name, the second column name now is renamed to C2. Okay. Now let's look at exercises. This is pretty straightforward. We talked about this previously. One thing to note here is if you look at the mean of the outcome here, right? The mean of this thing here. We have 4.49. So it's very close to 4.5. And what is the expectation of this binomial distribution? It is 9 times 0.5. So we expect to see 4.5 on average, we expect to see 4.5 desired outcomes in the long run, right? That's what expectation is. And here, when we do 100,000 trials, so a lot of trials, we do see the mean converge. It converges to 4.5, so the expectation. If we increase the size of trials, we will even get a number that should be even closer to the expectation, which is 4.5. Let's see. It's gonna take a while because this is a huge number, right? Yeah, maybe I should have chosen a smaller number here. Let's see. Let me kill this real quickly. Well, it doesn't let me. So let's do. Okay. So it's not, I think it is closer, but it's not significantly closer. Let's try this. See, this is when setting a seed is important because then we will produce the same result each time when we run this, right? So let's do this, 4.49, right? If we add two more zeros, 4.499. So it's a little bit closer. However, if we, let's try 1,000, right? And this is less closer, right? If we try 10, so this is, should be very far away from 4.5, most likely. 4.9, yeah. If we try 5, 5.4, which is pretty far off from the expectation, which is 4.5. Bar plot of the trials in the table above. We talked about this before. Bar plot for probability, right? Interactive analysis describe what each bar plot signifies, sorry, and how the two are related. So I'll leave this to you guys to do. Cube sum is also something that we did. We talked about this. I'll just show you guys. Now 50 trials of 4 flips, each for a fair and unfair coin. So, and whenever you see a fair coin, and you flip a fair coin, and you should think of binomial distribution, and you should set the probability to 50%, right? Because it's a fair coin, then we get the same opportunity, same probability to get the head and the tail. And an unfair coin, the probability most likely not going to be 0.5. Let's show the table here. Here. Create a contingency table of the above results, coin 2 and coin 3. You can also do the margin table. So the grand total and the row-wise sum and the column-wise sum. I also talked about this. The 100 here, 50, 50. Yeah. Now we can convert the contiguous table to one to the probabilities by dividing each element of the table by the grand sum, the grand total, right? Okay, here's everything for chapter 2 exercise. Thank you very much.